I'd like to start out by acknowledging my collaborators, and particularly Professor Bruce Robinson and his group, who have really pioneered the use of new statistical mechanical methods to simulate results of electrically poled materials, and also Christine Iserborn, who's collaborated with our research group on the development of new quantum mechanical methods, particularly methods that can be applied to materials in the solid state. So this is really calculating the properties of, if you will, organic clusters. I'd also like to acknowledge financial support from the Air Force and from the National Science Foundation. And I might note that this talk will focus on an overview of literature published in the last 2 years. I'm going to somewhat refrain from talking about unpublished work because some of my students, such as Christian Hafner, will be giving talks at conferences this year presenting new results, and I don't want to steal their glory. There have been some quite amazing work from some of the students working in our group. Today, I'd like to focus your attention on two grand challenges that are involved in this work. One is chip-scale integration of electronics and photonics, and the other is multiscale theory-guided design of organic electro-optics, or in general, soft matter materials. And I'd like to start out by sort of a perspective on chip-scale integration. I really don't have to say much because a variety of federal and National Academy workshops and technology assessment activities have made the argument for the importance of chip-scale integration. And in fact, groups such as Defense Science Board Advisory Group on Electron Devices, which is primarily focused on getting an industrial perspective, have emphasized that if photonics is to move from a niche market situation to actually having broad economic impact, chip-scale integration is probably critical to that. These technology workshops have also emphasized that if one is talking about chip-scale integration of electronics and photonics, electro-optic modulator technology is central and critical to this issue. And this brings us really to the topic of today, which is electro-optics. And I would note in this slide, which I've adapted from some of my collaborators and good friends at Boeing and Lockheed Martin, really emphasizes that one of the reasons you want to pursue chip-scale integration is because size, weight, power, cost, and performance is critically important. And as you might gather, as represented by these defense companies which focus on airborne and space applications, this type of technology is critically important once you start dealing with space and airborne activities. Well, if the objective is so critically important, why hasn't it already been achieved, since this has been recognized as important for more than a decade? Well, first of all, if we start with probably the best-known electro-optic technology, lithium niobate, one realizes that to start with, there's about a factor of 1 million mismatch in size between electronic and photonic circuit elements. That is, a lithium niobate modulator has a footprint of about 1 million times larger than that of current electronic elements, which are actually somewhat smaller than indicated here in general. Also, one of the tough obstacles to overcome is that you have to operate with digital level drive voltages for micrometer scale, length scale devices. And that means you really have to have very large values of electro-optic activity to achieve this. Likewise, you have to operate with femtojoule energy efficiency. You have to have high signal linearity, that is, bit error ratios for digital processing and spur-free dynamic range for analog processing. You have to have high bandwidth, at least greater than 100 gigahertz, and something that's normally not talked about, but is very important when you're talking about large-scale integration, is that you have to have low optical insertion loss for devices. And of course, target performance values will vary with application and with who you talk to. So I've taken what are, I think, some generally agreed upon values, although in some cases the argument would be made with like even lower values. For example, footprints, you want about 1 micrometer squared. Voltage linked products, less than 10 volt microns. Energy efficiency, less than a femtojoule per bit. Bandwidth, greater than 100 gigahertz. Bit error ratios, less than 10 to the minus 9th. And optical insertion losses of less than 4 dB. Although it would be argued by engineers, the lower the better. In fact, we'd like to have no insertion loss, which isn't obviously practical. Well, what have we achieved thus far? And for this, I based this on a recent article published in ACS Photonics that's cited here. And footprints of less than 20 micrometers squared have been realized. Voltage linked products are in published work is at 40 volt microns, although recently, and this is some of the work the students will be talking about, even lower values have been achieved. Energy efficiency is typically around the femtojoule per bit, even though there are publications of somewhat lower values. The current bandwidth stands at about 170 gigahertz, and the best bit error ratios are a little less than 10 to the minus 13th. And optical insertion loss is a problem, and currently the best values reported in the literature are somewhat less than 6 dB, but I note that Christian Hafner has actually recently achieved values as low as 1 dB, but with an extinction ratio of about 15 dB. Okay, this actually gives you a comparison of technologies. We mentioned lithium niobate, but that isn't actually a very good comparison with modern state-of-the-art, because lithium niobate has a relatively low electro-optic activity of roughly 32 picometers per volt, and the processing of that makes it very difficult to integrate with modern hybrid integration techniques and achieve these micrometer scale devices. So a better comparison would be with quantum confined Stark effect devices, Frank Kurdish effect devices, and free carrier dispersion devices. And this particular slide gives you a comparison of these technologies over time, comparing two aspects of the work. One is the bandwidth, and the other is size. And I've only compared two general sizes. The larger symbols represent sizes of around device lengths of around 100 micrometers, and the smaller represents about 10 micrometers. And as you can see, recently with organic-based hybrid devices, both silicon organic hybrid devices, SOH devices, and plasmonic organic hybrid devices, one has started to achieve both substantial bandwidth and also very small device sizes. And you might ask, how have these advances been achieved? The ones that I've alluded to on just the previous slides. And there are really two aspects of this. One is the improvement of materials, and the second is novel device architectures. And I'd like to basically talk a little bit about both of these. And I'd like to start with the optimization of electro-optic activity and other properties in organic electro-optic materials. And multiscale theory-guided design has been critical to this. It's produced new material concepts, and it's produced dramatic improved performances. In fact, in devices currently, the electro-optic activity is 300 to 400 picometers per volt, and in bulk materials, it's about 500 to 600 picometers per volt in published literature, but actually the current values are about twice those. So there's been a dramatic progress in the last couple of months. And in this next few slides, you're going to see exactly how that's achieved and where we can actually go. There are a lot of new concepts that have come out of theory-guided design. And there are two aspects to theory-guided design. One is the use of quantum mechanical methods to actually improve calculations of hyperpolarizability, including strongly interacting chromophores at high number density in the solid state. And the second is new coarse-grained statistical mechanical methods. So first of all, I want to briefly tell you about the modifications that have to occur in theory. Obviously, fully atomistic calculations aren't capable of dealing with this level of complexity. And so you have to do coarse graining to speed up run times and to actually carry out a tractable simulation of experimental results. Well, first of all, the upper slides show you here that you get just as good a results with coarse graining methods as you do with fully atomistic methods. And with organic materials, you have to somewhat move away from using simple spherical coarse graining that is common with other types of materials to using coarse graining that involves shaped molecules. And also you have to use a level of detail that takes into account the critical features of molecules, for example, that the molecule is non-linear. This type of advance has proven to be critically important. Another important evolution of coarse-grained statistical mechanical methods is to deal with the problem that you encounter both experimentally and theoretically, that molecules tend to hang up because of strong interactions in non-equilibrium configurations. And one way to get around this computationally and to gain insight into the kinetics of material processing, for example, electric field polling that occurs in real systems, is to use what we call the adiabatic volume adjustment method, which really mimics the condensation of materials from solution or the gas phase. And so what you do is you start carrying out calculations on a less dense system and you just allow it to condense. And that tends to dramatically reduce the tendency to hang up because of strong interactions. Well, theory has produced some dramatic new insights, and one of the first and most obvious is that we all thought initially that electric field polling dropped off and went to zero as you increased concentrations of chromophores in polymer materials. All the earlier work was focused on chromophore polymer composites. But theory actually, and this is what you would see for low dipole moment chromophores. So you get electro-optic activity here only at low number densities over here, and it's basically a center-symmetric structure at the higher number densities. But as you go up to higher dipole moment materials, which is what happens if you make better and better chromophores, because dipole moment as well as hyperpolarizability increases for these materials, you find that a second maximum in polling-induced acentric order occurs at higher number density. And you also learn that you can dramatically affect this as you might anticipate, because at high number density, short-range interactions, short-range steric interactions, packing interactions become very important. And as you see here, as we modify a chromophore shape, you can dramatically increase the effective electro-optic activity, which is directly related to the product of number density times acentric order. You will note if you look at this particular slide, the acentric order continues to increase as you go to the most extreme modifications, but you start to lose electro-optic activity because you're reducing number density here. Theory also showed that shape, I show you the results for linear chromophores here, but shape is very important, and in fact you get dramatic influence of, for example, nonlinear shape on this type of simulation result. And so the coarse graining theories have led us to new classes of materials, high number density materials, and other classes we'll talk about shortly. And it's also emphasized the subtleties of chromophore design and shape on electro-optic activity. And this is one of the reasons it's taken so long to optimize electro-optic activity in material. Theory has also shown that we can introduce other dipolar and quadrupolar interactions into the materials that can influence the lattice density of the material, as, for example, the introduction of Coumarin units here. This is a theoretically generated two-dimensional lattice image of chromophores shown here in red and blue colors. And this is the Coumarin type units, which drive at two-dimensionality. And theory tells you as you reduce the dimensionality of a material, you dramatically improve electro-optic activity. Well, this simply shows you that theory can give you quantitative simulations of results. And if you look carefully at results here, comparing AVA with conventional MPT, statistical mechanical calculations, you can find that you can identify kinetic problems in the tendency of materials to hang up in non-equilibrium aggregates. Quantum mechanically, what we've shown is that you get the best optical electro-optic activity when you have dipole moments of about 1 and subtle variations in steric interactions that control the torsional angles can lead to dramatically improved electro-optic activity. In fact, about a factor of 4 over what we achieve with the currently best chromophore systems. Well, I just want to quickly go through devices, and this basically illustrates in this upper figure the reduction in size as we've gone from all organic devices to integrating organic materials into silicon structures where you've cut silicon waveguides where you've cut a slot in the material and you filled that slot with organics, all the way down to plasmonic devices where you basically have organic sandwich between two metal electrodes. And I also want to use this slide to illustrate how you build up more sophisticated architectures. What's shown here are phase modulators. So you apply an electric field, you control the phase of the material. You can put two phase modulators together to form a Mach-Zehnder modulator, which allows you to modulate amplitudes, and you can put two Mach-Zehders together to produce an IQ modulator, which is the workhorse of telecommunications because it allows you to both control phase and amplitude, and so that allows you greater density of information coding. Also, I wanted to show you for the silicon organic hybrid devices that one of the advantages is you concentrate both electrical and optical fields in nanoscopic dimensions, which greatly enhances the electric field intensity in devices. And you can do the same with plasmonic modulators. There you, of course, have to convert from a photon into a surface plasma polariton, and that's done, for example, with structures such as I show you here. I also show you a phase modulator, a Mach-Zehnder modulator, and an IQ modulator. And again, with plasmonics, you concentrate fields, both electrical and optical, in these nanoscopic dimensions. Of course, one of the advantages of plasmonics is that the very low RC time constants allow you to get very high bandwidth, and you can obtain very small sizes. The problem is optical loss, but there have been dramatic advances made in actually reducing loss. This is a relatively new observation that is critically important, and that it shows that as you go to small wavelengths, you start to see a dramatic drop-off of electro-optic activity, which impacts voltage length performance and also optical loss. And so what causes that drop-off? Well, theoretical simulations say that on the surface, okay, the chromophores lie down along the surface, and so that they can't contribute to the electro-optic activity. Indeed, in these types of materials, as a function of electric field, you can observe a Friedrichs transition analogous to what's seen in organic liquid crystals and discussed by Dejean. So it's a very rich field in terms of how you can improve electro-optic activity and continue to take advantage of this dramatic electric field enhancement. Well, these are the three contributors to dramatically improve device performance, and I won't take time to run through them. I just want to emphasize that in addition to telecommunication devices, there have been a lot of developments in sensor devices. There are devices that avoid optical losses associated with going from photonics to plasmonics through silicon waveguide structures. There are beam steering devices, more sophisticated devices. Comb sources have been generated, difference frequency generations, frequency shifters. And finally, chip-scale integration has been done. And this just shows you the polling, processing, as well as operational device structures. And finally, we have device and theory publications. And I'll conclude with simply giving you this summary slide, which simply tells you what is next. Thank you.